Welcome to part 5 of a 6-part series where we will explore the Intel Quartus software JTAG debug tools. In this course, we will look at the JTAG debug tools that are available in the Intel Quartus software. First, I will go over Signal Tap. Signal Tap Embedded Logic Analyzer takes the brains and features of a typical external logic analyzer and incorporates them into your FPGA design, programmed into the target device on your board. It is an embedded logic analyzer built using available FPGA resources, no I/O, board routing, or probe points required. The Signal Tap Logic Analyzer emulates many of the features of an external logic analyzer. It taps signals within your design, meaning it samples, captures, and stores on-chip internal signal data values. This is done on the rising edge of a specified sampling clock. Signal Tap gives you the unique ability to monitor deeply buried design signals in real time during normal system operation. You're able to control and view captured data on the fly through a standard JTAG connection, typically used for programming the device, or in some cases, remotely over a network. The Signal Tap ELA is available for free and included automatically with a standard installation of the Lite, Standard, or Pro editions of the software. A version of the Signal Tap control interface is also included with the standalone programming software, allowing you to control and monitor the ELA without a full installation of the Intel Quartus Prime software, though without the ability to reconfigure its settings. You can find this at the Intel FPGA Download Center. Based on how the logic analyzer works and how it is implemented, it's easy to see when you might want to use it and when you actually can use it. If you don't have any external test equipment available, such as multimeters, oscilloscopes, or logic analyzers, the Signal Tap Logic Analyzer is a great replacement. As mentioned, you need available logic blocks to implement the logic analyzer itself, and you need memory blocks to store captured data samples. In most cases, you must have a direct active JTAG connection to the device under test to control the logic analyzer. Typically, this makes use of an Intel FPGA download cable. However, if your design includes a network connection, remote access for debugging over a network may be possible. We'll look at these additional connection options later. One of the most important details to understand about debugging with the ELA is that you can only perform a functional debug. Any timing delays inherent in the design will not appear in the captured data. This makes sense since data is only sampled on the rising edge of the sampling clock, hiding any timing information that may occur at other points in the clock cycle. It's helpful to look in a bit more detail about how device resources are consumed by the logic analyzer. Signal Tap uses device logic elements and memory block resources for its implementation. However the logic analyzer is configured, it must fit in the device along with the main design being tested. The amount of logic required is based on the number of signals, or channels, monitored as well as the number and complexity of the trigger conditions. The amount of memory used is determined by the number of monitored channels as well as the sample depth, meaning how many samples are captured and stored in the memory buffer for each channel. The more channels monitored and the deeper the sample depth, the more memory blocks are required to implement the logic analyzer. In theory, for each instance of the logic analyzer, you can capture up to 2048 channels with up to 128K samples of each channel. However, an ELA of this size would require 13,127K blocks to store all the captured data. Even the largest Intel Stratix 10 device has only about 11,020K blocks. Thus, you can make a logic analyzer instance as big as needed, but you will probably be constrained by the size of the device before you get anywhere near maxing it out. Later, we'll look at the storage qualification feature, which lets you make the most efficient use of the limited buffer space available in a device. In the standard edition of the Intel Quartus Prime software, as you make changes to the logic analyzer configuration, a resource usage estimator constantly updates to keep track of the number of resources required. This helps identify if you need to simplify the tool's configuration because your device is running low on available resources. Here is a summary list of the main features of the Signal Tap Logic Analyzer. The ELA provides the ability to debug multiple clock domains simultaneously by instantiating multiple instances of the logic analyzer in one project and controlling them all through a single interface window. As already mentioned, the tool lets you capture a large quantity of sample data for as many channels as needed, limited only by the availability of device resources. For triggering options, the logic analyzer can monitor up to 10 different trigger conditions, sequentially or in any order you choose with the state-based triggering feature. The external triggering features make it easy to interface the logic analyzer with other devices or logic including the hard processor system on SoC devices. The trigger conditions themselves can be basic Boolean and or triggers or advanced triggers in the form of more complicated Boolean expressions. The signal tap logic analyzer makes it easy to create almost any type of triggering condition. To make effective use of limited buffer space, you can enable data storage qualification. With this feature, captured data samples are either stored in the buffer or dropped depending on selected conditions. Finally, the data captured by the logic analyzer can be stored in many formats and exported for use in other applications, such as simulation, power analysis, or design documentation. We'll discuss most of these features in this training, but check the Intel Quartus Prime Debug Tools user guide and the Intel FPGA website for more details about these and other features of the tool. Links to these resources will be provided later. There are two ways to add the logic analyzer to a project. The first way is to create a signal tap file with the file extension STP and enable it in the project settings. This is the easiest way to implement the ELA and is recommended for most debugging situations. Once a file is created, multiple signal tap instances can be added to and controlled with a single file. When the file is saved, it gets automatically enabled for the currently open project. The file can be edited, enabled, or completely disabled and removed from the currently open project in the signal tap project settings. The other way to add the logic analyzer is to create it as an IP instance using the IP catalog and IP parameter editor. The signal tap IP is found in the basic functions category of the IP catalog under debug and performance. The IP parameter editor for the logic analyzer allows you to adjust all the basic parameters needed to create a single signal tap instance. The resulting output from the parameter editor then needs to be either instantiated in the design, with the signals to tap specified in the port mapping, or added as a component in a platform designer system design. The ELA implemented in this manner can be controlled from a command line or by creating a related STP file using the option shown. Removing the logic analyzer from the design requires removing the IP instantiation and recompiling. If you would like more information about implementing the signal tap logic analyzer using this method, see the Debug Tools user guide. Creating the STP file alone is in general a faster and easier way of implementing the ELA, so this training focuses exclusively on signal tap usage with the STP file. Creating a new signal tap file is simple. You can select Signal Tap Logic Analyzer from the Intel Quartus Prime Tools menu, create a new file and select Signal Tap Logic Analyzer file from the Verification Debugging Files category, or click the Signal Tap Logic Analyzer task in the Tasks pane. The default name for a new signal tap file is stp1.stp. Use Save As from the File menu to rename the file, if desired. Once your device is programmed with your design and the Signal Tap IP instantiated inside, you can launch Signal Tap through the Tasks panel or from the Tools pull-down menu. The main Signal Tap file window has a number of different panes, each with its own function. The Instance Manager includes controls and indicators to work with individual or multiple Signal Tap instances. The highlighted instance or power-up trigger in the Instance Manager is the active instance. Changes to the settings in other areas of the Signal Tap file window only affect the active instance. To switch to an inactive instance, double-click the instance in the Instance Manager, or use the Instance tabs at the very bottom of the Signal Tap file window. To quickly create new instances, right-click anywhere in the Instance Manager and select Create Instance. You can rename instances by either clicking on the instance name or right-clicking and selecting Rename Instance. The status column during Logic Analyzer configuration will always be Not Running, but that will change later once the Logic Analyzer starts analyzing and capturing data. The Health Monitor at the top of the Instance Manager, currently at Ready to Acquire, indicates the overall status of all Signal Tap instances and whether a recompilation is necessary to integrate updated Signal Tap instances into the design before they can be run. Finally, the Analysis control buttons next to the Health Monitor control how each instance is run to watch for the triggering conditions. The node list on the Setup tab in the Signal Tap file window is used to select signals from your design for monitoring, as well as for constructing the actual trigger conditions. To tap a signal, simply double-click an empty area of the node list to open the standard node finder. Bus groups added to the node list can be expanded, as shown here, to change settings for individual signals within the group. Even if signals are not part of a bus, you can create custom groups in the node list for organizational purposes, or to create trigger conditions based on the different groups. Just select the signals you want to group by Shift or Control-clicking them. Right-click and select Group. You can also organize signals any way you want and move signals into existing groups through drag and drop. With an advanced trigger, you can create more complicated logic expressions for trigger conditions, giving you more control over the trigger's definition. You select to create an advanced trigger using the trigger type list at the top of any trigger condition column in the node list. When a column is set to use an advanced trigger, a new tab is added to the Signal Tap window. Switching to the new Advanced Trigger tab opens the Advanced Trigger Condition Editor, a simple graphical interface for defining an advanced trigger expression. In this editor, drag and drop tap signals or groups from the node list and attach them to logic-defining objects to form a trigger expression. The advanced trigger occurs when the expression defined at the top of the editor evaluates to true. The result equation at the top of the editor constantly updates to represent the expression defined by the objects placed in the window. Any signal or group of signals can be dragged out of the node list and dropped in the main window, but only trigger-enabled signals are listed. Objects such as comparison or logical operators can be dragged out of the object library list. Double-clicking an object lets you adjust settings specific to that object. Objects with a white background, such as the greater than, less than, and value objects shown here, can have their settings adjusted during runtime without recompilation. Objects in the editor automatically connect together when they are placed near each other. Right-clicking empty space in the editor window gives additional options, such as the ability to zoom in and out of the editor, automatically clean up the placement of objects, as well as center the objects in the display. The editor is very flexible and intuitive, making it easy to create complicated expressions. When the trigger occurs, the captured data is stored in the memory buffer, transferred to the Signal Tap file, and displayed in the Data tab. The Data tab is the main interface for immediately viewing captured data. The Logic Analyzer will automatically switch to the Data tab when data is transferred from the buffer, so even if the trigger did not occur, you can still view what was in the buffer when the Logic Analyzer was stopped. By default, the horizontal scale of the display indicates buffer sample numbers, one for every rising edge of the sampling clock. You can right-click the scale and select time units to display actual time delays between captured samples. When viewing sample numbers, the sample captured at the trigger is considered sample 0, and pre-trigger data samples, samples captured in the buffer before the trigger occurred, have positive numbers and are displayed to the right of the trigger. Post-trigger samples have negative sample numbers and are to the left of the trigger. If the viewing of data discontinuities for storage qualification is enabled, a feature we'll look at later, extra markers are displayed to indicate where samples were skipped from being stored in the buffer. By default, the Data tab provides a waveform display of all the data-enabled signals in the node list. Group signals have data displayed in a radix of the user's choosing. You can change the radix or view the group signal data in different ways, such as a bar or line graph, by right-clicking on the signal group name in the column on the left and selecting a view option. Controls in the Data tab make it easy to move around the captured data quickly. The trigger position is indicated by a dashed line located at data sample 0. Everything in the waveform display is referenced to the master time bar, a thick black bar that is initially placed at the trigger position, but can be dragged anywhere in the data. The numbers above the master time bar indicate the current segment in a segmented buffer and the current sample within that segment. We'll look at the use of a segmented buffer later. The previous and next transition buttons will move the master time bar to the next or previous transition of a selected signal. One or more reference time bars can be added to the display by simply clicking at the top of the view. Reference time bars indicate their location with respect to the master time bar. The top number indicates the segment difference between the master and reference time bars in a segmented buffer. Reference time bars can be used to measure the time between signal transitions or certain events. Left-clicking a waveform zooms in to make it easy to see individual samples. Right-clicking zooms out. If the trigger sample is not visible because of a zoom-in operation, select Center Waveform on Trigger from the View menu to shift the trigger sample to the middle of the display. All other basic configuration of the Logic Analyzer is performed using the Signal Configuration section of the Signal Tap file window. The Signal Configuration pane is where you specify a sampling clock, set the characteristics of the selected instance's memory buffer, and configure the use of triggers. You can configure these options either before or after you've tapped signals and set up trigger conditions. If you have used external test equipment before, such as oscilloscopes or logic analyzers, some of the settings configured here should be familiar. At a minimum, a sampling clock must be selected. Use the highlighted Browse button to open the Node Finder and select a sampling clock for this instance of the logic analyzer. For situations where the FPGA design under test may be at a remote location, either somewhere on your local area network or across the internet, the Signal Tap Logic Analyzer supports remote debugging. For an FPGA design that does not include a network connection, you can set up a computer-to-computer debugging session. For this setup, the local machine you will work on must have a full Intel Quartus installation. The remote machine must be set up with a connection to the board under test, typically a JTAG connection using a USB blaster, and either a full Intel Quartus installation or just the Intel Quartus programmer. The JTAG server feature is then enabled on the remote machine in the JTAG setup found in the Signal Tap file window or the Intel Quartus programmer, allowing the local machine to connect to the remote machine. You can then run the logic analyzer as if you were sitting in front of the board under test. You can also perform remote debugging by connecting directly to a remotely running FPGA design without the need for a remote machine. For this configuration, the FPGA design must include some type of microprocessor control, such as a Nios 2 soft processor or the ARM hard processor system found in Altera SoC devices. The microprocessor is necessary because the design must be able to set up and control a TCP/IP stack for a direct network connection. For more information on this type of remote debugging configuration, focusing on the use of the HPS, see Application Note 693, linked here. The captured data can be exported to the multiple file formats listed here for use in other tools, or for documentation purposes. Export the captured data using the export command in the Signal Tap or Intel Quartus Prime file menu. A different way of viewing the captured data is through the creation of the list file. A list file is a simple text file where each row corresponds to the signal states of all the signals within a single captured data sample. The key at the top along with the columns and column headers indicate what the signal level is for a particular signal within a particular sample. This makes it easy to see the raw captured sample data generated by the logic analyzer. The Signal Tap Logic Analyzer can be fully controlled through the command line or scripted using tickle commands. The command line can be used to enable or disable a particular Signal Tap file for a project. You can also compile a design that includes the logic analyzer, start and stop an analysis, as well as control multiple Signal Tap instances simultaneously. The command line scripting chapter along with the Signal Tap chapter, both in the Intel Quartus Prime Handbook, have a number of examples of how to run Signal Tap from the command line or a tickle script. Before compiling any project, you need to set up timing constraints in one or more SDC files. If your design includes a JTAG-based debug tool, like Signal Tap, you should add timing constraints to your SDC file for the JTAG interface. You can do this relatively easily using the highlighted template, available from the Intel Quartus software text editor when editing an SDC file. The template is documented in the Timing Analyzer Cookbook. Add the template to your SDC file and customize it for your own use. Next, I will go over In-System Sources and Probes. The In-System Sources and Probes editor in the Intel Quartus software allows you to easily control any internal signal and provides you with a completely dynamic debugging environment in which to generate stimuli and solicit responses from your logic design. ISSP operates over JTAG and can source and probe up to 512 signals. You can use ISSP when all you have available is a JTAG connection and all you need to do is to monitor signals or send logic values into signals. You can even use ISSP in conjunction with Signal Tap so that you can force a trigger condition to happen so you can gather data on the signals of interest. To use ISSP, first locate the IP in the Intel Quartus software and add the IP to your design. Adding the IP will cause the IP parameter editor to launch. Configuring the IP is straightforward and only requires the probe port width and the source port width. Once configured, use the generated instantiation template so that you can instantiate it in your design. Afterwards, run your design through the entire compilation process and download the bitstream to your FPGA. After the bitstream is loaded into your FPGA, you can access the ISSP core through the JTAG connection. And launching the ISSP editor from the Intel Quartus software tools pull-down menu. Once you have done that, you will interact with a GUI similar to one shown here. The Instance Manager helps manage the instances of ISSP that you have in your project. The JTAG chain configuration lists the JTAG devices that you have. And the Sources and Probes is where you can send your logic values into your project and then monitor the signals through the sources connection. An example of an ISSP use case is connecting up the ports of a reconfigurable PLL to the source's signals and make on-the-fly changes to how the PLL operates. The last JTAG debug tool that I will go over is the In-System Memory Content Editor. The In-System Memory Content Editor allows you to quickly view and modify memory content either through a GUI interface or through Tcl scripting commands. The In-System Memory Content Editor works by turning single-port RAM blocks into dual-port RAM blocks. One port is connected to your clock domain and data signals, and the other port is connected to the JTAG clock and data signals for editing or viewing. Use cases for modifying memory contents are to artificially inject errors to test error correction mechanism in your design, try different coefficients for filter, modify video data stored in memory, and so forth. You use In-System Memory Content Editor on single-port RAMs and ROMs. The second port of the memory is used to communicate through the ISNCE system over JTAG. When you create your memory, go to the Mem Init tab and select the checkbox to allow In-System Memory Content Editor to capture and update content independently of the system clock. Specify an instance ID so that you can identify between the various types of in-system modifiable memories and constants. After your design is complete and your memory is instantiated, do a full compile and download the bitstring to your FPGA. The JTAG connection to your FPGA board will connect to the second port of your memories. Once your FPGA is configured, launch the ISMCE from the Intel Quartus Software Tools menu, and a GUI similar to the one shown here will come up. The Instance Manager gives you details of the attached memories. JTAG Chain Configuration shows the details of the JTAG chain. The Hex Editor is where you will type in the memory changes that you wish to make, as well as get a readout of what is current in memory. You can read the values from your memory when you first launch the GUI. Red numbers indicate that the RAM-ROM values are not current. After launching the In-System Memory Content Editor, click the Read button to update the Hex Editor with the RAM/ROM values. Use the Hex Editor to change the number in the RAM-ROM. Blue indicates that the values are to be written. Pushing the right button will change the numbers red again, which means that the values in the RAM-ROM are not current. And then pushing the Read again will update the Hex Editor with the current values. There is also the continuously read button, which will constantly update the Hex Editor with the contents in RAM-ROM, and then the Stop button will stop the continuous read cycle. But you don't have to rely on the built-in Hex Editor to send and receive data. You can import memory data by using either the hex or MIF memory initialization file formats, so you can create your memory files offline and then upload them as needed. You can also export the data in a variety of formats so that you can capture the information that you need, and then do a thorough analysis of the data offline. You are also not limited to using just a single instance of the In-System Memory Content Editor. You can have multiple editors open accessing different FPGAs in the device chain. To help in automating your testing environment, you can script ISNCE using Tcl. To summarize, I went over the JTAG debug tools that are available in the Intel Quartus software, namely Signal Tap, In-System Sources and Probes, and In-System Memory Content Editor. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5-minute quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live, instructor-led course presented either in person, at an office local to you, or virtually over the web. All instructor-led courses have hands-on labs exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages, called landing pages, dedicated to specific FPGA technology like and high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA application engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. Thank you for listening to Part 5 of the series, Intel Quartus Software JTAG Debug Tools. Check out our other 5 parts in this learning series.